Welcome to the third talk in our celebration series about contributions of GBO to various scientific fields. We are really excited to have this talk be in person. So welcome to everyone online and welcome to those of you in person. So those of you online, we've launched a poll, so please fill that out just for some interesting topics. So we've heard some talks about GBO's contribution to galaxy evolution via the 21 centimeter line. Also heard about GBO's contribution to pulsar research. But today we are very pleased to have Dr. Brett McGuire here to tell us about the contributions of GBO to the exciting field of astrochemistry. So Brett McGuire received his BS in chemistry from the University of Illinois at Urbana-Champaign in 2009 and his PhD in physical chemistry from the California Institute of Technology in 2014. He was an NRAO Jansky Fellow and then a NASA Hubble Fellow from 2014 to 2020, and at the Center for Astrophysics, Harvard and Smithsonian. In 2020, he started a faculty position at MIT, where he's now the class of 1943 Career Development Assistant Professor of Chemistry. Research in the McGuire Group uses tools of physical chemistry, molecular spectroscopy, and observational astrophysics to understand how the chemical ingredients for life evolve with and help shape the formation of stars and planets. So thanks so much, Brett. We're looking forward to this.
Sure. Thanks for that introduction. Thanks everybody for showing up and showing up online. Hello, everybody. I want to start by saying that I have had more fun preparing this talk than anyone that I've ever given in the past. It was an absolute blast. As a result, I spent way more time preparing the talk than I should have, so I have never practiced it. The presentation may be a little rough, but I hope you'll find all of the little bits and bobs that I've dug up to be interesting. Two more caveats. I'm neither a historian nor an astronomer. I just played these things on TV today. So 100% historical accuracy not guaranteed. But let's go ahead and dig in. So I want to start with my definition, if I have the mouse in the right place, of the field of astrochemistry. We'll get a much more authoritative one here in a little bit. But I define astrochemistry as the study of molecules in space, where they are, how they got there, and what they're doing. And chemistry occurs at every single step along the process of forming stars and planets. All right, so you can go all the way back to the Big Bang. Right, this produced hydrogen and helium, as we all know. A smattering of lithium and beryllium is a treat, right? But that's about it. It wasn't until the first stars were born of that elemental hydrogen and helium and processed them that the elements that we think of as driving chemistry today, organic chemistry, making life, carbon, oxygen, nitrogen, phosphorus, sulfur, were really synthesized and put out into the interstellar medium. Now, those elements at some point will form the next generation of stellar nurseries where new stars will form. But even before those stars form, at 10 Kelvin, in the cold, dark clouds of gas and dust that GOTHAM is studying. I'm here with my GOTHAM team this week, right? Studying a dark cloud at 10 Kelvin. Chemistry is happening. Surprisingly complex chemistry can happen even at these coldest places. And then when a star turns on, it injects heat and energy into the system. Right? And that drives chemistry even further, both on the surfaces of dust grains and in the gas phase. We now know, of course, that around almost every single one of these stars, planets will form, and those planets are being constantly bombarded with the early chemical remnants of their natal molecular cloud. Right? Even today, meteorites crash down on the surface of the planet and bring the chemical remnants of the molecular cloud that we formed in. On at least one example that we know of, life arises from those chemical elements, and then eventually, no matter what, that life and everything else will be consumed in some sort of fiery cataclysm of one kind or another, and all of those elements will be ejected back into the stellar life cycle to start the process all over again. And chemistry is happening at every single step along this process. So as far as I'm concerned, the goal of astrochemistry is to understand on a detailed molecule by molecule, reaction by reaction basis, how we go from hydrogen and helium to cats, right? Start to finish and then destroy them, which is kind of fun. So how are we doing in studying chemistry in space? Well, this graph is accurate up to like 6 days ago. we detected 267 individual molecular species in space. And this started all the way back in the early 1930s. Now, these detections back here were performed using ultraviolet or visible absorption spectroscopy in line of sight clouds, right? And they were almost discovered by accident. Optical telescopes looking at background stars and seeing absorption lines in the diffuse gas between us and that star. And it took quite some time for the community to accept that these molecules, diatomics consisting of 2 atoms, existed at all, right? Because space is really harsh. It's a harsh environment. And the predominant theory at the time was that everything will be blown to bits. Even if you make a molecule, it's going to be blasted apart. Right? So folks debated and went back and forth for a while, eventually agreed that yes, we were seeing molecules, but they were going to be a rarity, right? Just these few diatomics that were robust. And that kind of held for a while, because for the next 30 some odd years, we had a dark age of molecular discovery. No new molecules seen in space outside our solar system. Folks looked at UV and visible spectroscopy, just didn't see anything. It wasn't until after the war, when radio telescopes started being built, that we actually started detecting molecules in earnest. First one there was OH, followed shortly thereafter by ammonia, and the one that's going to be the most pertinent to us to start our discussion, formaldehyde here, H2CO. So here's the list actually updated as of a few days ago to include our latest detection, which we'll talk about a little bit later. 268 molecules known outside our solar system. And because we're in Green Bank, I'm going to highlight the ones that are really important here, the ones that were detected at GBO. Right, so the ones in blue were all discovered with the 140-foot telescope for the first time outside our solar system. All the ones in red were discovered with the Green Bank telescope for the first time outside our solar system. If I plot this up in a timeline here, right, you can see that this really came in 2 different chunks, right? 140-foot really dominated for quite some time. And then there was a gap, another dark age there, right? Before the next generation came along, the GBT came online and started providing new molecular detections for us again. Now, I'm not going to talk about it because it's not at Green Bank, but there was another NRAO telescope that really dominated for a while somewhere in the Southwest. But it's not Green Bank, so we're not going to talk about it. All right, so let's take a trip back in time. Once upon a time, back in 1969. All right, this is the first molecule that I can find discovered here at Green Bank. All right, so this is formaldehyde. And I put the paper up here. This is by Lou Snyder, David Beal, I don't know how to pronounce that name. I think it's Barry Zuckerman and Pat Palmer here. All right, discovered with a 140-foot telescope. All right, and here's their spectrum. They took in absorption toward the galactic center, just pointed straight at Sagittarius A. All right. 4.8 gigahertz, which, if you read the paper, was implied to be extremely high frequency at the time. All right, the 111 to 110 transition of formaldehyde. And what we're seeing here, this is not hyperfine or anything like that. These are just differential absorptions from different line of sight clouds between us and the galactic center. All right, so I want to point out something interesting here as well. All right. This is something that Snyder says later on in the paper. We regard the close coincidence of the astronomical and laboratory rest frequencies as a strong argument in favor of the identification with formaldehyde, since we find no other molecule composed of astrophysically abundant elements that has a microwave line with rest frequency that lies within our error bars. Some other molecule is found that has an astronomically measured rest frequency, a conclusive identification will require detection of other microwave transitions of either molecule. And I point this out because this really is the first iteration of what have become known as Snyder's rules, Snyder's laws for detecting new molecules in space, right? These lines don't come with a tag for what they're coming from, right? There are other molecules in space. They weren't able to isolate just formaldehyde in the cloud, right? If something else had been there and been absorbing at these frequencies, then it would be hard to tell, right? So Snyder in 2005 down the line, again, not necessarily with the GBT, so not talking about it here, set out a set of rules for definitively identifying molecules in space. And 2 of them are, in fact, the one most important one is no other molecule has to have rest frequencies at the same location. And then the second one is you need to have multiple transitions of your same molecule so that you're getting that frequency pattern from the rotational spectroscopy exactly. And this is going all the way back to 1969 in the first paper saying, look, we did our due diligence. The observation was really hard, so we only looked for one line. And if something else comes up that could suggest this is something else, we have to go find other lines of the molecule in order to be correct. Second molecule came around not that long after, so this is in 1970 by John Ball here, and a name a lot of folks in the audience might recognize here, Carl Gottlieb, looking at the detection of methanol. So at a much more reasonable frequency, 834 megahertz, right? And this was a big deal for a couple of reasons. One, this is a really, really complex molecule, especially by the standards of the day. Remember, we had gone from diatomics to atoms. Now we're all the way up here at 6 atoms, right? That's quite a bit. This is also an Earth relevant molecule here. And something else that I want to point out is that not only was this line observed in emission, remember the old one was observed in absorption. So now we're actually looking at the emission of molecules, right? But this is one of the first records that I could find showing the importance of having high spectral resolution to resolve these lines, right? Now, high spectral resolution here was 192 channels, right? That was the full spectral resolution of the receiver at the time. Now we're using hundreds of thousands of channels in Vegas, and I want more. Thank you, please, right? 192, right? But it really was necessary. This is a pretty thin line, right? And you want to resolve that profile and actually see what you got. But something else really stood out to me in this paper. And that was, this was one of the first instances that I found that had a direct reference to laboratory work within the same team on the same paper, right? Which is an integral part of astrochemistry today. The back and forth between laboratory spectroscopists measuring the frequencies of these molecules and observers looking for them. Well, here they said they went and thought they found it in Sagittarius, but they weren't entirely certain of the frequency of the line, right? It had been extrapolated from earlier measurements or calculations. I forget which one which. So they said, look, we have Carl Gottlieb, a real laboratory spectroscopist on our team. We're just going to go into the lab and measure it ourselves, right? And so this is one of the earliest instances, in fact, it may be the earliest, I'm not entirely certain, of an astronomical detection that relied both on observations and laboratory work in the same paper. All right. Now for some of the fun stuff. This made headlines, believe it or not. It made a lot of headlines, right? So I went back and dug through newspaper archives. It's all over the place, not just methanol and formaldehyde, but detections of a whole bunch of different molecules. There were a string of them that came out between 1969 and 1972 or so that really made headlines across the globe. So some of these are in the Boston Globe. Some of these I got from Iowa, Birmingham, Alabama. They're all over the United States. And they're not just copy and paste articles either. Individual reporters were coming out here, interviewing staff at Green Bank, interviewing the scientists, and writing up the excited way that folks were talking about this new regime of chemistry and astronomy that was happening in space. So I want to zoom in on 2 of these here. So the first here is Harvard scientists spot alcohol near the Milky Way, and I want to show you how they describe methanol. Methyl alcohol is better known as wood alcohol or torpedo juice, apparently. Right? The substance in illegal liquor, which was temporarily or permanently blinded venturesome youths during Prohibition. Right? Because if you make moonshine and you do it poorly, you don't distill things properly, methanol is what's left over. What they don't tell you is that the treatment for methanol poisoning is just more ethanol, right? Because the ethanol preferentially binds in your blood and kicks the methanol back out. So if you have methanol poisoning, they'll put you on an ethanol drip when you go into the ER. I don't recommend it. It doesn't sound fun. But then here from Stanton, Virginia, actually, the Stanton, Virginia leader back in 1970, quotes from Lou directly, right? So many space scientists are already speculating about the chemical implications of interstellar clouds of complex molecules, how they might fit into an evolutionary pattern of life throughout the galaxy. All right, so that life cycle was being discussed all the way back here at Green Bank within the first couple of years of these detections. Of course, no one knows how far astronomers will be able to go with their detections of new molecules, but it doesn't appear as though the end is in sight. And he was correct, of course. Something else was fun, though. This really was the birth of astrochemistry as a field. And I didn't believe it, but the newspapers said it, right? So astrochemistry shows up as a word for the first time in papers back around 1970. Do clouds in space hold secrets of life? A new science is born, astrochemistry, right? It promises a treasure chest of new understandings about the origins of Earth and life. And this wasn't just, some random paper reporter who was talking to Lou and got excited about the name. No, we got several pages, full spreads from Isaac Asimov himself. The field of astrochemistry was introduced to the public by a many-page spanning essay from Isaac Asimov on the possibility of life in space, how we are able to investigate it now, look at it now that we're detecting molecules outside our solar system, right? And he described what the field of astrochemistry looks like. Now I pulled this particular chunk here because it's still a little funny today. It looked as if the chemists might not be kidding themselves. Did that mean if we looked harder and in more detail, we might find such important compounds as amino acids, building blocks of proteins? No, not yet, right? That's still our white whale there, right? But it probably is coming. Right? The ability to detect amino acids is probably just over the horizon. Now, I don't know whether or not, I wish Tony was here, but he's in an AUI board meeting. So he could tell us whether or not Lou was just being a little pretentious or whether or not he thought this was actually what it could be called. But apparently Lou Snyder didn't like the term astrochemistry, right? So he said, these are being studied in an emerging new branch of astronomy called astrochemistry, or more correctly, astromolecular radiospectroscopy. Right? Which sounds like he was just trying to toot his own horn, but I don't know. All right, that kind of sounds like it. But I like astrochemistry. Sorry. All right, so we'll move on ahead here a few years. So 1971 to the microwave detection of interstellar formaldehyde, or formamide, I'm sorry, which stood out to me for a couple of reasons. We're still with the 140-foot here, of course, right? This is, I believe, the first molecule ever seen with the 4 main elements necessary for life, right? Carbon, hydrogen, oxygen, and nitrogen, all in the same molecule. Now, this isn't terribly biologically relevant. It's fairly poisonous, right? But it is interesting, right? You now have all of the elements necessary for life bound up in a single molecule. A couple other things that I wanted to point out. Well, we're back up at high frequencies, 4.6 gigahertz here, but 2 interesting things. This is one of the first complex molecules where we're starting to see, starting to make the identifications, not just based on the frequency coincidence of one line, but on the hyperfine splitting of that line. Right, the characteristic splitting in the rotational frequencies due to the unpaired spins in the nitrogen nucleus of this element here. They're characteristic of the molecule. They have a splitting pattern which is well defined by quantum mechanics, and it's unmistakable. So it adds extra credence to this molecular detection, even if we only have one line. I also thought it was fun. This is one of the earliest papers where I can find actually written out the equation for calculating the optical depth of a line and the Coulomb density of a line of a molecule from rotational spectra in radio observations. Of course, it was known prior to this. Some of the earlier papers do quote Coulomb densities. This is one of the earliest ones that spells it out nicely. And these formalisms are still built on and written out in our papers today. The equation hasn't changed all that much, nor should it, right? It's a function of quantum mechanics and statistical mechanics. I just thought it was interesting. It's one of the earliest places that I've seen it. Now, formamide here, because it had all 4 elements, did indeed make international headlines this time and even got its own comic strip. All right, so this is from, I believe, Sydney, the Sydney Herald or something, talking about not just formamide, but talking about the discovery of molecules in general. But the fact that it contained all 4 elements really set off this new firestorm, or as they put it, a gold rush in the sky, right? So, they point out, although formamide plays no role in any terrestrial life form, it's the nearest molecule yet found in space to the amino acids. We are hearing about amino acids again that we still haven't solved, right? But it's quite interesting. They also make a statement back here alluding to the earlier distrust of the community in making molecules in space, right? Astronomers are still puzzled how such molecules can survive the fierce disintegrating bombardment of ultraviolet and cosmic rays in space, which I think is interesting. Now, there is one grievous error in this comic. We've all been looking at it for a little while. Has anybody spotted the grievous error in this comic? Because I'm going to show you the correction that had to be published immediately the day after, as they received calls of complaints. It's right here. The structure here is a little wonky, as it turns out. So I said they apologize here. The illustration showing the components of a formaldehyde molecule was not intended to be a formal molecular diagram. Such a diagram would, of course, have shown a double bond between the carbon and oxygen atoms. Yeah. Anyways, of course, it was intended to be a formal molecular diagram, but that's okay. They're covering their oopsies. All right. Oh, forget I don't have wireless receiver here again. All right. So we'll move on again, right? Those were relatively normal molecules by terrestrial Earth standards. But if we jump ahead a few years now, so now we're in 1978, right? We're looking at the detection of HC9N in interstellar space, 2, 4, 6, 8, 9. Yes. The low frequency, now real, well, I say low frequency, extremely high frequency line, right? Was done with the Algonquin 46 meter of Canada. But the confirming transition and the higher signal to noise transition had to be got here at the NRA 140 foot, because the Algonquin performance at that high frequency again was not very good, right? So it all came down to GBO for that second transition. But this is a weird molecule, right? Way more atoms in it, and unlike anything that the synthetic organic chemists here on Earth were familiar with. Right. Again, even today, when I show these molecules to my actual chemist friends, they look at me like I'm crazy. Like, you can't make this. It's unstable. It's highly reactive. It's going to disappear and give you cancer while it does. Right. But this again made headlines. Right. Heavy molecules discovered in space. Much more accurate diagram this time around. Right. But I pulled out two interesting snippets here that I want to talk about. More important than the weight alone is the now increased awareness that since molecules of such size exist in space, somewhere in the dark and mysterious dust clouds between stars may be real amino acids. Again, we're still on the amino acids. All right. More important for this clip, though, the three heavy molecules, this was just one of them, right? They also had HC7N and HC5N at that point, have all been detected within one such cloud located approximately 350 light years from Earth in the constellation of Taurus. That cloud is TMC1. That's what my GOTHAM team is studying with a large project on the GBT. I'm going to tell you why that's important here in a second. I do want to just point out over here the team that made this discovery. So we have Lauren Avery and John McLeod at Algonquin and at GBO here, who did the observations on HC9N. The rest frequencies came from Takeshi Oka, who many of you may know from University of Chicago, right? But the latest discovery is an extension of earlier laboratory work by Harry Kroto, University of Sussex. If you don't know Harry Kroto's name, right, he was famous in the laboratory, one, for doing laboratory experiments, trying to figure out how you make these molecules, right? So here's a paper that actually was delayed. The timeline here is a little bit flipped, right? But here's a paper that was delayed a little bit from laboratory work, where what they were doing was examining the formation of these molecules by taking a carbon rod in the laboratory and just hitting it with a laser, right? Giving it a ton of energy, vaporizing the carbon into the gas phase, mixing it with some nitrogen or hydrogen, right? Forming those end caps, and then seeing the products that came out. This was the product that came out. C60, Buckminster fullerene, right? This is the Nature paper from Harry Kroto's discovery of this, and this is the abstract here. During experiments aimed at understanding the mechanisms by which long-chain carbon molecules, HC9N, discovered here at GBO, were formed in interstellar space, TMC1, right, studied here at GBO, graphite was vaporized, and they made C60. They weren't looking at C60, it just showed up in their mass spectrometer. All of the carbon basically formed into this one C60 molecule. Now, if you're not familiar with C60, at least terrestrially, this along with maybe one other experiment, is the genesis of the nanocarbon revolution. So everything to do with graphite and large carbon sheets, right, and carbon-based conductors, right, that was all launched because of the detection and discovery of C60 and a couple other things around the same time, which was only found by accident because somebody came here to GBO and found a weird molecule in space, right? Which I think is pretty cool. I also point out, if you read the end of the Nature paper here, I just think it's pretty funny. Croto says, "We are disturbed at the number of letters and syllables in the rather fanciful but highly appropriate name we have chosen in this title to refer to C60. They suggest that it should be named something more concise. Nothing ever stuck, right? Buckminster fullerene is just too much fun to say, right? So buckyballs." They also made one more prescient observation here that's more relevant to astronomy. Even more speculatively, C60 or a derivative might be a carrier of the diffuse interstellar lines. So here's a newspaper clipping from the time talking about the discovery of C60, right? Scientists see Bucky as a stellar performer here and its potential relevance to what's going on in space. It's possible that Bucky molecules have been producing great quantities in space, especially in carbon-rich stars. It's also possible that rich supplies of Bucky molecules in interstellar dust clouds may account for peculiar light absorption patterns that astronomers have recognized in such clouds for decades. So what they're talking about, if you're not familiar with that, are the diffuse interstellar bands. Right, so these were discovered by Mary Lee Hager as part of her thesis project, and never given credit for the discovery because she was a woman in 1920 whatever doing the work. She found them almost by accident because she noticed that they show up in basically every sightline that you look at in our galaxy that has diffuse material between us and a background star. Right, they're sharp, they're distinct, they're bright, they show up everywhere. And until about 5 years ago, out of the hundreds and hundreds and hundreds that there are, we had identified none of them, right? It's been said by some to be the longest standing spectroscopic mystery in the history of mankind, right? To date, we know of the carrier of two. These two here at 9.5 and 9.6 nanometers, bad with wavelengths, and they belong not to C60, but to C60 plus, a derivative of C60, just as predicted by Croto and that original paper talking about the discovery of this molecule, right? So this was some really fantastic work done by Ewan Campbell and John Meyer back in 2015 it is now, so 7 years ago now. We don't have another, this is it. It's these two and one other that's been assigned to C60. So if anybody else wants to discover more diffuse interstellar bands, please do. I'll note that it's been said that there's no faster way to ruin a scientific reputation than to speculate on the carriers of the diffuse interstellar bands. So proceed at your own risk. All right, so we're going to move out of the original series now. The last detection of a molecule with 140 foot was C5s in 1993. Now, there's this intervening space here where there were other telescopes operating at Green Bank, right? In particular, this telescope, the 300-foot telescope. Right? The 300-foot telescope never detected a new molecule in space. Right? It wasn't designed for that, right? But its collapse, right, as the telescope fell down, and here, I'll point out this picture here is apparently Wes Sizemore here, looking at the 300-foot telescope's remains here, right? Spurred the production of a new telescope that really is going to revolutionize our ability to detect molecules at Green Bank. This is what spurred the production of the GBT. Right, so Phoenix-like, a telescope is to rise from a pile of metal. So this was a really nice expose here, or write-up from, where was this? The Richmond Times-Dispatch in 1990, right? Talking about the death of the 300-foot and the future rise of the GBT. And whoever is the editor responsible for laying out this did a really good job because this article was placed in the obituary section. Really fantastic. I want to point out something fun here. This was in 1990. By 1995, the $75 million telescope was supposed to be ready to map the undiscovered universe by listening to the radio waves. So here I have a picture from the unveiling of the GBT in 2000, right? When the commissioning first started here. I will point out that this lovely photo here that has the GBT in the background, also has a cameo from the Sci staff of the day, down out in front of the field. I haven't seen any cows on GBO property in my entire time here, which is pretty funny. Was it I don't even know if it was an active working farm nearby where this photo was taken from. But it's an excellent picture of the telescope. There's also, in a similar article, an excellent picture of Phil Jewell at the time, who was interviewed in a lot of these different articles talking about the construction of the GBT. He was, I think, assistant director. The public was also really interested in the GBT. It's pretty cool. This is a quote from Katie Aguilera, who recently led a group of 12 and 13-year-olds looking for an adventure on a rainy day. So apparently it feels a bit like walking into Star Wars to come see the GBT. So few fits and starts didn't come on in 1995, didn't even really start in 2000, but first molecular detection started rolling off in 2004 from the group of Hollis, Jewell, Lovis, Remingen, and where's the last one on there? Arstock-Mallendahl. All right. Now, these were propenal and propanol here, two molecules of, they're just more complex. There's nothing horrifically exciting about them chemically, but interesting things to point out. Right? These are really weak signals, and they're at really high frequencies relative to what the 140-foot could do. Right? So it's showcasing the power of the GBT as a new molecular discovery machine. These also made headlines. So here's the write-up in the Star Telegram on Monday. Scientists, this is below an article about Shaquille O'Neal. Scientists announced the discovery of two new molecules in the center of the Milky Way, propenol and propanol. These are not considered to be as significant parts of the Milky Way as the previously discovered chocolate and caramel. Only headlines for these molecules that I could find, but still the public was interested. Right? But over the next few years, this team in particular really started churning out discoveries of new molecules with the GBT, all leveraging the power and sensitivity, spectral grasp, high resolution of the GBT, its instruments, and its backends. Maybe the most exciting thing at the time was the detection of the first anions in space. So this was led by Mike McCarthy and Pat Thaddeus up at the CFA. They got the C6H minus, the 8H minus, a few CN minus molecules as well. Anions are not very common in interstellar space, and there's still kind of a mystery of how they're formed. So this is sort of living on today. So now I'm going to segue to one of the projects that I've worked on tangentially. That's the Primos project, right? That Tony Remingen set up. He was part of that team of Hollis, Jewell, Lovis, Remingen, right? It was surveying molecules in the galactic center. So this was, I think, the first, or at least the broadest and deepest spectral line survey for astrochemistry done with the GBT. It was a large project set up to survey the galactic center, so Sagittarius, B2N, at that time, unprecedented spectral resolution and sensitivity. And it continued to pump out new molecular detections. So we have ethanamine, transmethylformate, cyanomethanamine, protonated isocyanic acid, propylene oxide, and carbodiamide, all coming out of this survey of Primos. Thank you, Tony. So I'm going to dig, we'll come back to headlines here a little bit at the end. I'm going to dig in just a little bit and talk about one of these because it was one of my detections, propylene oxide there. So the really cool thing about propylene oxide is that it's a chiral molecule. And that means that the two mirror image versions of this molecule are non-superimposable on one another in 3D space, right? So they're like your hands, right? Your hands are mirror images of one another. But if you try to overlap them in 3D space, there's no way you can rotate or translate them and get them to exactly line up. Right? Palms are facing up, your thumbs are in the opposite direction. Thumbs line up, palms are in the opposite direction. Right? So this is a property of any 3D object, or many 3D objects, called chirality. It comes from the Greek word chir, for hand. And molecules have this property too. Right? So here's a molecule. It's so important that it has its own Wikipedia page. This is bromochlorofluoromethane. It exists only to demonstrate chirality. As far as I can tell, it has no other purpose. But you can imagine projecting its mirror image here, right? So the dashed lines here are things going into the plane of the screen. The wedge line is coming out of the plane of the screen. And if you can imagine rotating the one on the right so that the bromine lines up, well, then that chlorine there is pointing out. and the fluorine is pointing in, right? Again, you can't rotate or translate them to get in the same orientation. And this has unique chemical properties. So these interact with other chiral things uniquely. So one-handedness interacts with a chiral thing differently than the other handedness does. Right? It's just like trying to put a left-handed baseball glove onto a right-handed hand. It just doesn't work. So here's an example of a molecule called carvone. Right? The left-handed version here, designated as S for sinister, because left is of the devil, is the distinct flavoring and smell of caraway seeds. Right? And the right-handed version, identical molecule or atoms bonded together in exactly the same way, just a mirror image, is what gives us the taste and smell of spearmint. Right? Just same molecule, mirror image, taste and smell is completely different because the taste and smell receptors in your body are also chiral. Right? So they lock in and interact differently. And it turns out that all life on Earth has opted to use only one enantiomer, one-handedness, of most biologically important molecules, amino acids, sugars, and other such things. There's no particular reason for that to happen, right? We could just as easily have used all one-handedness of the other version, right? They're identical. So long as you pick one, you can still do all the same biological processes. So why the heck are we one-handedness versus the other? Well, of course, we might want to look in space to see whether or not we inherited more of one-handedness or the other, but we hadn't detected a chiral molecule in space until Primos and the GBT, right? So back in I guess it was 2014, when we first saw these lines, right? We were looking through Tony's data of the GBT Primos survey, and we took 2 absorption lines of propylene oxide exactly where they should be. Now, it's modern day times, and Snyder's laws apply more heavily now to transitions, generally not enough, right? You want a few more bits of information, and the next brightest line was here, the 110 to 101. That's at the lower end of KU band, and I believe that's a direct TV satellite. Unfortunately, it's just RFI interference from Green Bank, nothing that we could do about it. Turns out the Australians don't believe in television, however, and so if you go down to Parkes, you can get the line almost exactly where we predict it should be, and buddy up right next to it is propanol that we talked about right there, that original detection with the GBT. So let's spend the last few minutes here talking about our most recent survey. This is the reason that folks are here this week visiting Green Bank, and that's observations looking at this source, TMC1. All right, so this is the one that we were talking about from Harry Kroto's discovery, right? At this point, it has overtaken SAGB2N, right? From the Primos survey, more new molecules have been detected in this place than anywhere else in the galaxy, anywhere else in the universe, right? About 1 in 3 molecules are discovered for the first time in TMC1. It's located around about there in the dusty lanes in the constellation Taurus. So our project that we have set up on the GBT to study this is the GOTHAM project, GBT observations, TMC1 hunting aromatic molecules. Our logo is made of real aromatic molecule data, benzonitrile data that we're pretty happy with. This is an out of date, but mostly complete slide of our team here. We're made up of primarily, well, it started out as just postdocs and graduate students and Tony, and has since expanded to a wide variety of students and collaborators across the United States and across the globe, actually, broadly spread into the observational laboratory and modeling areas of astrochemistry, all dedicated to trying to understand what molecules are present in TMC1. What new chemistry can we discover in this source where Harry Kroto was spurred to find C60? So this is the product of all of our GBT time on TMC1 so far. It's a high sensitivity, high spectral resolution spectral line survey spanning, actually we have some S and C band data that are on here all the way up through the upper end of Ka band. And we're making this data publicly available as soon as the observations are finished. We said that at the beginning, hoping that the different frequency chunks would get done in a reasonable time span, and they didn't. So only X band is available so far because it's the only one that finished. But you can go grab that from our paper in AppJ or just ask me for it. And then as soon as we finish reducing these, the last observations were taken in July of this year. Those will be online and available for you to download and use as well. So the GBT, true to its name and Green Bank's legacy, has been no slouch in detecting new molecules with this survey either. Right, so this is a rogues gallery of almost every molecule detected for the first time in TMC1 using the GBT, using just this one survey, right? It's an incredible array of new molecules. A lot of them look similar to those carbon chains that Croto was interested in all the way back when. But I do want to bring your attention to these molecules down here in particular, and I'll add the fourth one that we just published a detection of last week. These are 1 and 2 cyanonaphthalene and indene and cyanoindene, these large molecules with these 2 fused rings involved in them. These are aromatic molecules, and in particular, they're polycyclic aromatic hydrocarbons. These are molecules that have long been thought to be present in interstellar space. There's been circumstantial evidence, very strong circumstantial evidence in the infrared since 1986 or so. But these are the first times that we've ever identified individual ones outside our solar system, which is exciting to us as chemists because it allows us to start probing how they actually react and evolve. Depending on who you ask, something like 25% of all carbon in the universe is contained in molecules like this, in polycyclic aromatic hydrocarbons. So they're hugely important in interstellar chemistry. Now, I said I would get back to headlines, and I just want to draw your attention to 2 final headlines here. The first is, this did make headlines, at least virtual headlines. Is a really nice piece written up by Jill Molesky here at Green Bank, among a few others. But I had a really fun time because I found, or it was sent to me, somebody grabbed, I think it was Jill's press release, I'm not exactly sure whose, clearly translated it using Google Translate to a foreign language, and then translated it back to English so that it would pass through the copyright filters and they could get their clicks. So I just want to read you a few excerpts from the other headlines. Within the place we discovered them, there is no such thing as a star, so they're both being constructed up in place, or they're the leftovers of a useless star. I think that was meant to mean an old dead AGB star, but we'll give them that. Now, they are useless, sure. We did this work using the Inexperienced Financial Institution telescope. Apparently, that was fantastic. And the analysis staff additionally contains scientists from a number of different establishments, together with the College of Virginia, bad, the Nationwide Radio Astronomy Observatory, so we're an insurance agency now, that's fine, and NASA's Goddard House Flight Middle Space Flight Center, which I thought was pretty fantastic. So I just have one slide left here, and then I'm going to end a little bit early for a specific reason for those of you that are here in the audience in person. But just what's next? And I said this at the K-band workshop earlier in the week, but for us, for astrochemistry, for molecular discovery, science scales linearly with bandwidth, right? One of the huge advances that I showed you here was the Primos project and the Gotham project. And they both were able to substantially increase the number of molecules that we got because of the broadband capabilities at high spectral resolution, right? That is what allowed us to get all of the molecular signals that we needed in a reduced amount of observing time, rather than having to look for one line at a time with 192 channels per polarization on the 140-foot telescope. Oh, I lied. I had one more thing here. Radio telescopes listen on the rim of the universe. This is back in 1970, describing why radio telescopes are so great. Well, radio telescopes can see more than 10 times further into space than optical telescopes. They were developed as an offshoot of radar equipment used during World War II and were received by scientists with all the glee of a child confronted by a fascinating new toy. And if anybody ever asks you why you do radio astronomy instead of optical astronomy, this is what you should point them to. Radio astronomy is essentially the same as the science as regular astronomy, study of celestial bodies, but it is so much more sophisticated than astronomy that the interrelationship is like that between calculus and arithmetic. For radio astronomy's prime tool, the radio telescope is to a regular optical telescope as an optical telescope is to a magnifying glass. So radio astronomy rules. Absolutely is the case for detecting new molecules in space. 90% of all molecules in space are found with radio astronomy. And a huge, huge portion of that started here at Green Bank. So thank you very much for your attention. I'll leave up here the ways you can get in contact with me online. My new group here at MIT, who are all here, so please find them and chat with them and introduce yourselves. And I'm happy to take questions that you might have as well. For those of you that are here, afterwards, I printed out the full page articles of every news clipping that I showed today, a huge spread of them. So I'll spread them out so you can read through all of the newspapers, full articles if you'd like. Thanks.
Thank you so much, Brett, for that extremely entertaining and very informative presentation. So what we'll do is we'll alternate between questions in the in-person audience and the online audience. So do we have any questions in person first? Jay.
Yeah, the sky, the Milky Way has been studied in a lot of surveys, and you've got a lot of information to go on before you start looking for molecules. Is there anything in that data that would have told you the TMC one was the place to look?
A priori, just a history of detecting carbon-rich molecules there, I think is the answer. I mean, my understanding of the way that that source selection was built up to begin with, and I could be mistaken here, was that the thing to do was to start pointing your telescope at the pretty places in the sky that were shown to be rich and complex by optical astronomy. Right. And so Orion and Sagittarius, right, are obvious candidates for that. TMC1, I think, turned out to be interesting, both by some early radio mapping, not particularly looking at molecules, but also because it's a dark place in the sky, right, that the optical light can't get through. And so it's an interesting place when you have a new technique to just point a telescope at. Once molecules started being found, it's pretty evident in the literature that folks just honed in on a single source. And you might then do a small map of it once that became efficient and find something else nearby that was more interesting. But I think I would say there are certainly places on the sky as rich and as interesting as TMC1 that we haven't found yet, just because nobody has stumbled upon them yet or has done the early work necessary to find them. I don't know if that answers your question or not. Thanks.
Jesse, do you have anything online?
Yep, so we have one comment and one question.
Okay.
Firstly, the comment, it reminds this individual of an early computer translation from English to Chinese, back in English, out of sight, out of mind, became invisible idiot.
Like it? Tony, you just walked into the room.
And then we have a question unrelatedly. So are amino acid detections still being conducted, or is there some reason they haven't or shouldn't be detected?
Yeah, folks are still looking for amino acids, and it's a fine way to motivate things. So the spectrum of glycine, so the simplest amino acid, the one we're most likely to detect, is incredibly complex. There's a lot of lines, and they turn out to be pretty weak. The chemistry of glycine is such that we're only going to see it we're most likely going to find it in the star forming region, lots of other complex molecules, and a lot of energy. And that means that there's a lot of other spectral lines there from a lot of other interesting and complex molecules. There's not going to be a lot of glycine, because it is so complex, so its transitions are weak. It's really hard to identify a region where you can find clean transitions of the molecule that are not confused with something else, where there's enough of it produced by the chemistry, and where your observations are at the right frequency and at the right spatial resolution to isolate it. I would guess that glycine has a decent chance of being detected within the next decade or so using ALMA or maybe the NGVLA, decent being, I don't know, 20 or 30%. But the more complex ones are going to be even harder. Yeah.
Okay, any in-person questions? Or in-person
Yeah.
So when you search for one of these molecules, how much do you know a priori? Can you calculate where
Where the lines are going to be?
the line should be, or do you have to go into a laboratory, size these, or what's the ratio?
Yeah, so I think the ratio is probably 97% of the time you need to measure them in the laboratory first. Calculations will never give you the frequencies accurately enough to find them exactly where they will arise in space. For some very simple linear molecules that have just a few transitions, and it's line and then an equal spacing, equal spacing, equal spacing, so very regular pattern. In a few instances, calculations have gotten you close enough that you can recognize that pattern offset by your error. right? We can identify a few molecules that way, but everything else has got to be done in the laboratory. I think it was molecular hydrogen. It was really fun. It was detected first in space by sending a sounding rocket up, an aerobie sounding rocket up with a spectrometer on the back of it, looking at the sky. And then when the rocket crashed, they took the spectrometer off the rocket, went into the lab and measured the hydrogen signal with the same spectrometer that they used to measure the signal from space off of that rocket. And it's the only time it's been done with the same instrument, but it was really cool.
We have another online question.
Not for, okay, however, I'll suggest a question that has been asked at previous talks by the director, Jim Jackson, which is, if you could have any brand new instrument to your specifications on the Green Bank telescope, what would it be?
Yeah, so those of you that are at the K-band meeting, sorry, you've heard all of this before. But I just want a receiver that covers the entirety of a spectral band and a back end that digitizes the whole thing at less than a kilohertz resolution simultaneously. That's it. 1 pixel, all of K-band, 18 to 27 gigahertz at 0.5 kilohertz resolution. That would be great.
Any other questions here in person? Jay?
So what's the ratio of the two hands of that molecule?
Oh, that's a great question. We can't tell. Now, we thought we might be able to originally because chiral molecules interact with chiral light in different ways too. So if you shine circularly polarized light, any polarization light, and separate it out into its two polarizations on a asymmetric ratio of a chiral molecule, you'll see more of one-handedness of light be absorbed than the other. It's called circular dichroism. Signal is very small. Now, there was a paper in 1992 that suggested that propylene oxide, and in particular the transitions we detected, would have very strong circular dichroism signal, something that would show up in the GBT at a fraction of a percent, so not within our current capabilities, but maybe within future capabilities. A theorist revisited that after our detection and published a paper about 2 months ago that said that it's something more like a part in 10 to the 9 of a percent that you would need. So we can't do that measurement. What we'd like to do with the NGVLA, however, is an indirect measurement of the excess. So the way that an excess of one would be generated in space, we think, is by selective destruction of one-handedness versus the other by an excess of UV circularly polarized light. So UV light that has an excess of one-handedness versus the other, it will interact more strongly with one-handedness of the molecule than the other and destroy that more strongly and generate an excess. And that is a process we can measure quantitatively in the lab. We can figure out the cross section. If you expose this much molecule to this much radiation at this excess, you'll generate a 2% handedness of one or the other, right? So what we'd like to be able to do is use the NGVLA to map precisely where propylene oxide is in the cloud, and then use UV observations to map precisely what the excess of one-handedness of UV circularly polarized light or the other is in the same place, and infer whether or not you could generate any significant abundance that way. It's a hard experiment, many years down the line, but it's a potential avenue to do that. But for now, we don't know. I will say that chiral molecules detected in meteorites, most of them show a 50-50 mixture, but there are a number of chiral amino acids and other molecules found in meteorites that show an excess of one-handedness, and they always show an excess of left, which is the one that we are, right? It's a small excess, but it's always left, which is pretty cool. Suggestive, I would say.
I got a question.
Sure.
How did you find all these fantastic newspapers?
Newspapers.com. Yes, which the reason I didn't practice anything is because their free trial lasted like 4 days, and then they were going to charge me $50 or $75. So I had that span to just sit at my computer and spam through these. But it's great. It's all OCR recognized, the text for everything. It works really well. So I'll lay them out outside and on the tables here. You guys can keep moving through.
Okay, any final questions? Okay, well, let's Brad get